remember, as usual, there's a quiz. This one on galaxies. So the quiz has been open since yesterday, but we'll finish on galaxies today. So we'll still have plenty of time to finish the quiz on galaxies. I'm starting to get some emails about people worried about their grades. I want to note, remind you, I always drop the two lowest quiz grades. So if you miss two quizzes, or just if you have two low quiz grades, I will drop those. Also, in order to help you out, some of the quizzes are more than 20 questions. I will grade them out of 20. So even if there were 22 questions, I will end up, if you get 19 out of 22, I'll give you 19 out of 20. So that should help you out. And I'll do the same. I'll drop the two lowest participation as well. So if you miss two classes, I will drop those participation points from your grade. Any questions at all about how things are going? Okay, so where we left off, we talked about the types of galaxies. We talked about elliptical galaxies. We talked about spiral galaxies, and the fact that it's not just two types, it's really a spectrum of types of galaxies, but we have two kind of classifications, broadly speaking, spiral type and elliptical like. And then there's irregular galaxies that don't really fit into any criteria. What I next wanted to do is zoom out even more, right? In this class, we've started out close to our solar system and keep zooming out. So in addition to just galaxies, there are, just like there's groups of stars, clusters of stars, there are groups of galaxies. So let's talk about the types of groups of galaxies. And we have different names. The smallest group of galaxies is just called a group, something like a dozen, something less than 50 roughly galaxies. And our own Milky Way is part of a group. That's a group that includes our own galaxy, the Milky Way, and Andromeda, and the galaxy called Triangulum. And overall, it's about 50 galaxies, covering about 10 million light years. If we zoom out even further, there are clusters. We give the name cluster for something that's more like 1,000 galaxies. And these are all gravitationally bound. These are all galaxies, just like how stars orbit around in a galaxy through gravity, right? They're all the gravity of millions and millions of stars are all pulling on each other, so they're all orbiting around the center of the galaxy. The same thing is true of galaxies themselves. They are orbiting around each other. You have a cluster, that means that there's a lot of gravity. The stars in one galaxy are pulling on the stars in another galaxy, so they form kind of like a little solar system, but instead of a solar system, it's a orbiting galaxy. And then if we zoom out even further, we have superclusters. And this is getting to be so large, it's not necessarily that these galaxies are even gravitationally bound. There's just, if we zoom out to the kind of the furthest distances, we do see clusters of clusters. Okay, we call those superclusters. Our local, so meaning the supercluster we are part of, it's called Laniakea. It's about 33 million parsecs, or over 100 million light years across. Okay. And we have a name for what we call, our local group is part of the Virgo cluster, and the Virgo cluster is among many clusters in this supercluster. And then when we talk about, right, we talked about spiral and elliptical galaxies. Spiral galaxies are more often found in groups, that is smaller numbers, whereas elliptical galaxies are more commonly found in large, really big clusters, hundreds to thousands of galaxies. Show you some examples, right? This is our own little local group, includes the Andromeda galaxy here and Triangulum. Okay. And remember, groups of galaxies tend to have spirals. So here we're seeing more often, not only spirals, but more often spirals, and just a handful of galaxies. This is called the Draco group. The Leo triplet, Ixen 44, Ixen 87. Okay. Here, let's just count them up. I see 1, 2, 3 spirals and 1 elliptical. Mm-hmm. The Virgo cluster. So here now it's a cluster. So this is a lot of galaxies, and now you see they're mostly elliptical, fuzzy shape without the disk. That's elliptical galaxies. So here, because it's hard to see, because anytime we look out at galaxies, we're also seeing all the stars through our own galaxy. So here I've kind of circled a lot of these galaxies in the Virgo cluster. The Fornax cluster. Here's one spiral, but most of them, as you can tell, as usual in clusters, is ellipticals. The Hydra cluster. Again, so here's a spiral, but mostly elliptical, elliptical. And then some stars. Again, it's always complicated by these stars. A Hercules cluster, also called Able 2151. Able 427, the Perseus cluster. So in summary, from last lecture and so far this lecture, there's three major types of galaxies. We have spiral galaxies, elliptical galaxies, irregular galaxies. And just as a quick reminder, spirals have both this thin disk, right? Think of our Milky Way. There's that disk where there are the spirals themselves, and then there's kind of the central fuzzball, okay? But if you were to just take away the disk, that central fuzzball is what is very similar to an elliptical galaxy. It's almost like elliptical galaxies are just kind of if you took away the disk, you're left with an elliptical galaxy. And ellipticals tend to have colder stars. They tend to be redder. Remember, in the disk, that's where you have a lot of star formation happening. That's where you see dust, right? You see those dust lanes. That means remember we talked about that. That's where stars are born, from that gas and dust that make up the interstellar medium. Okay, and then so spirals tend to be a little bit bluer from those, and remember that's because high mass stars outshine the other stars, and high mass stars are bluer. So if you do have these blue stars that are outshining all the others, then your galaxy looks blue. But those die off very quickly, remember, because they have short lines. So in ellipticals, you have older stars, as we're not birthing new stars. You tend to be left behind with redder stars. Okay, and then finally, spiral galaxies tend to form smaller groups.
No, I'm in class. What do you want?
Elliptical galaxies you see more often.
Did you not go to?
Clusters.
I thought I gave you to gym.
Oh, I did. I did it.
As a reminder of what we were just talking a second ago, ellipticals tend to be a little bit redder.
Go,
than average, right?
then good for you. You're on break. You're on food break.
Remember, this is a good just
Your lunch break.
Reticulars are kind
I
of
was just watching.
it's between spirals and
didn't.
ellipticals. And then there's irregulars.
Your
Those
teacher
are just
and you.
irregular.
Get out of here.
Now we're going to start moving towards the study of
Oh,
cosmology.
you're gonna shake your little butt.
Cosmology is talking about the universe as a whole. Okay, so as I mentioned, we're going to continue to zoom out in this course. And
No, shut up.
galaxies are kind of the basic component of the largest structures in the universe. So if we look out, if we zoom out as far as we can, we see galaxies, and we just talked about how they form groups and then clusters and then superclusters. But that's what you're looking at. So it really informs our study of the birth, the death, the life of our universe as a whole. And we'll talk about Hubble. Hubble was, his study of galaxies determined that the universe was expanding. So that's a big topic that we'll talk about when we talk about cosmology. The universe as a whole is expanding. But also we can learn things like the age of the universe. What was the past universe like? What will the future universe be like? And we can compute the age of the universe because of this Hubble's observation that the universe is expanding, which is something we'll talk about as we go forward today and then on Wednesday. And in order for Hubble and the people that came after Hubble to understand how fast, say, galaxies are moving, how far away galaxies are, you need to somehow determine distances to things that are really far away. How can you possibly determine the distance to a galaxy? And an interesting story is, not 100 years ago, people weren't sure that galaxies existed. they thought maybe the entire universe was just our own Milky Way galaxy. But we couldn't determine, they saw with their not as good telescopes as we have today, they saw these fuzzy things. They thought they might just be solar systems forming. They thought right? Because they actually are similar, right? Like you get these protoplanetary disks and things, right? We talked about these forming solar systems almost looking like little spirals, but they couldn't tell how far things were. So it was only when we figured out a way to determine how far things are that are really far that we could determine that, oh, some of these fuzzy things are way, way far away, millions of light years away. And that's how we started to learn about the universe as a whole. This is what we're going to go over today. It's called the cosmic distance ladder. And it shows as you move outward from our own solar system. So here's, say, the Earth, and you move out from our solar system to nearby stars, to the edges of our Milky Way, to other galaxies. How can we determine the distances? And the trick is, if we have one method and we discover another method, where they overlap, we can test them against each other. So that's why it's kind of like a ladder, right? We have one method and then another method that allows us to see a little further. We can test them to make sure they're both correct, and then another rung on the ladder, and we keep building further and further away. And so each of these methods here I'm going to describe about how we can learn just how far away things are. The closest things, like in our own solar system, we can measure very precisely using radar range. That is the same way like a police radar gun works, or the radar you see showing clouds, right? When you see a weather forecast, you just bounce radio waves off things and then they return. And you time how long it takes them to return because we know how fast light is. Remember, it takes about a second or two for light to bounce off the moon, say, and return to Earth. So we can figure out exactly how far away various planets are in our solar system nowadays. That's a more modern technology, but we can now. And remember, we also talked about stellar parallax. So for nearby stars, we have a really good way of learning their distances. And remember, that's because as the Earth moves around the sun over the course of a year, the Earth is moving very far. And when you move relative to things in the distance, things that are closer to you move more in your field of view. And so stars that are closer to us move across, whereas stars that are really far away remain fixed. The same way that when you're driving past a grain silo, the mountains in the background stay fixed, but the grain silo is moving past your field of view. It's the same principle called stellar parallax. And so we talked about how you can determine the distance in parsecs. Parsec stands for parallax arc second. That is, if you see a star move by an arc second in the night sky over the course of a year, that star is a parsec away, which is about 3 light years. We can't use radar ranging to find the distance to a star. That's just too far to bounce radio waves off of. In fact, remember, it would take years to wait for the radio waves to go and come back, and they'd be very faint by the time they came back. But for nearby stars, by far the most accurate way, it's very accurate, is to use stellar parallax. But already we're talking about a ladder, right? Because we know really, really precisely how big our solar system is using radar ranging. We can use really, really precise measurements to determine distances to nearby stars. Okay, what about further away stars? If we can determine a method to determine the distance to further away stars, we can cross-check that against, say, stellar parallax for nearby stars. So one way of doing that is shown here in this box. This is called main sequence fitting, because we talked about the HR diagrams. We talked a lot about how once you know the color of the star on the main sequence, you know how bright it is. And remember, what we can see about a star is called apparent brightness, right? But unless we know the distance to the star, we don't know its true brightness, because it could be far away or close. And this is the key to being able to figure out the true distance to a star if we know its apparent brightness and where it is on that HR diagram. So recall, this is a slide I've shown you before. The reason why there's a difference between apparent brightness and true brightness is that as you get further and further from an object that's emitting light, the light gets spread out over a larger and larger imaginary sphere. So if you think of a star here, further and further away, that light gets diluted, it gets spread out over an imaginary sphere of radius r. How big is that sphere? It's 4 pi r squared. So we said the apparent brightness is the luminosity, that's the amount of true brightness of the star, divided by the area over which that light gets diluted, 4 pi r squared. So the true apparent brightness goes down as the square of the distance as you are moving away from a light source. And so when we talk about this cosmic distance ladder for further away stars, if we somehow know what the true brightness of some type of star is, then we can use this formula to determine the distance, right? We measure the apparent brightness, B, and we know the true luminosity, L. We can then find the unknown, its distance. Okay? And we'll talk about so-called standard candles. These are called standard candles in astronomy. There's certain special stars we'll talk about called Cepheid variables. There's type 1a supernovae. These are these exploding low mass stars that have a specific brightness that seems to be the same roughly every time. And that then allows you, if you find one of these types of stars or supernovae, you can determine the distance to it because you measure the apparent brightness, you know how bright it actually is, and so you use this formula to get its distance. This is incredibly convenient. In addition, additionally, we have this HR diagram. Now remember, the beautiful thing about the HR diagram, and as a reminder, this direction is color or temperature of the star, right? Bluer is hotter, redder is cooler, which you measure by the color index.
Oh yeah.
And on the y-axis is the luminosity, the true brightness of the star as compared to the sun. So here's the sun yellow, it's 10 to the 0 or 1. But as you move upward, you get more and more luminosity. As you move downward, you're less and less luminous. And the great thing about the HR diagram is this diagonal represents main sequence stars. This is where most stars we see are on the main sequence. And so if we locate a star, say it's type B, so it's kind of a bluish star, we know what its luminosity is typically. Okay, type B stars tend to have this luminosity. We can just read it off from the HR diagram. So this is a way of determining distances, especially for a group of stars. So we talked about clusters of stars. There's the Hyades, there's the Pleiades.
7 sisters.
If you look at a cluster of stars, okay, and you draw its HR diagram, okay, you'll see the main sequence. It'll create a line of stars. And as an example, let's take the Pleiades and the Hyades. So if we put the stars of the Pleiades on an HR diagram, and we put the Hyades on an HR diagram, they both form one of these lines. They form lines. And here, what I'm drawing is not exactly an HR diagram. I'm drawing the apparent brightness of these stars. So without even knowing the absolute brightness of these stars, if we just plot the apparent brightness and the color, we see that they fall on these main sequences. And the only reason these aren't lining up is because one of these clusters of stars is further away from the other one. In fact, you can measure exactly using the formula we talked about above. Because the Hyades is 7.5 times as bright as the Pleiades, we know that therefore the square root of that, 2.57 times, is how much further the Pleiades is than the Hyades, which makes the Pleiades less apparently bright. Okay, so this is what astronomers use to determine. And again, this is like a ladder. if you know how far the Hyades are, which are closer than the Pleiades, then if you draw the color and apparent brightness of the stars in the Pleiades and match it up to the Hyades here, you see exactly how far the Pleiades are. So if you know how far the Hyades are, then you can figure out how far the Pleiades are. You can keep climbing up rungs of a ladder to get further and further away. So that's called main sequence fitting. And that gets us out to past thousands of light years away. That gets us out towards the edges of our own galaxy. Okay. So most of the stars in our galaxy, we can find the distances to using either stellar parallax for nearby stars or main sequence fitting for somewhat further stars. And then we have another overlapping method. So again, like a ladder, where there's special types of stars called Cepheid variables. And we can even see some of these stars in nearby galaxies, even though these galaxies are far away, it's hard to see individual stars. For nearby galaxies, we can actually pick them out because they have this particular property that they get brighter and darker with time, following a very specific pattern. These are called variable stars that are kind of unstable. They kind of, over time, follow this path. That is, they get kind of brighter and redder, and then fall back and get a little bit bluer and less bright. And they wobble back and forth like that. For nearby stars, we can determine exactly that this corresponds to a specific absolute luminosity. That is, the different luminosity corresponds to a different oscillation period of the stars. And then for stars that are further away, then we can trust this because we can test it for nearby stars. We can trust it for further away stars. As an example, Delta Cepheid. It's an example of one of these stars whose magnitude changes. Its luminosity changes over time. So here's a pattern of its kind of waxing and waning of brightness. And here's a graph just showing how good this works. So if we look inside our own Milky Way, we look to one of the nearest little satellite galaxies of our own Milky Way called the Large Magellanic Cloud. We can graph the luminosity versus the period, or how long it takes these stars to oscillate back and brighter, darker, brighter. And what you see is larger luminosities correspond to longer times between oscillating. And there's a very, very clear pattern. And so what's great is then if you locate a star a little further away, like an Andromeda galaxy that has this property, we can just use the slope of this line to determine its absolute luminosity. And then if we know its luminosity, by measuring its apparent brightness, we determine its distance. Any questions so far about the cosmic distance ladder? I want to give you a sense of scale. So we talked about earlier in the course, like if you represented the sun as a grapefruit, you know, how far away would the Earth be? It'd be like across the room, and it would be the size of the tip of a ballpoint pen. Okay, I can give you some sense of scale of the solar system. What about galaxies? Well, now if we keep shrinking everything, so the Milky Way, our whole galaxy is the size of a grapefruit. I want to give you a sense for how far away the closest major galaxy, the Andromeda galaxy, is to us. And the answer is that if you shrink our whole galaxy down to the size of a grapefruit, the nearest galaxy, Andromeda galaxy, which is also would be about the size of a grapefruit, would be across the room, about 3 meters away. And just in numbers, our own Milky Way is about 100,000 light years in diameter, and then Andromeda galaxy is about 25 times further than that, 2.5 million light. Now, who was able to measure the distance to Andromeda using Cepheid variables was Hubble. Okay, Here he is at the Wilson Observatory, measuring the distance to the Andromeda Galaxy. And what we're talking about here then is the discovery of Hubble's law. So Hubble used Cepheid variables to determine the distances to nearby galaxies, okay? And he discovered that there was a pattern, okay? And it's worth just mentioning Edwin Hubble in a little bit of detail, just because he is a local. He grew up in Wheaton, Illinois, and studied at University of Chicago, was a staff member of Mount Wilson Observatory, okay? And he discovered something hugely important that we'll talk about throughout the rest of this course, which is not only the existence of other galaxies by determining that some of these fuzzy things in the sky were in fact vastly further away than the stars in our own galaxies. So we knew that they had to be different galaxies entirely, and therefore learned that the universe was much larger than we thought. But further, he discovered a law, which is that the further a galaxy is from us, the faster it's moving away from us. In other words, anywhere we look in the sky, if we see a galaxy, if it appears to be moving away from us, which means it gets red shifted. Now remember, things that move away from us are shifted red. And the redder they are, the faster they're moving away from us. What you see is that the redder a galaxy is, the faster it's moving away from us, the further it is from us. And as we'll talk about in some detail, this means that the universe must be expanding. That is, in every direction, we see things moving away from everything else. Here's some of his early data. In 1929, here he was, just measuring the speeds of galaxies away from us. So positive numbers mean away from us, moving away from us. And you see there's some local galaxies close to us that are moving towards us, like Andromeda is actually moving towards us. Some are moving away from us. But as you move further and further away, so these are in millions of parsecs, so 1 million, 2 million parsecs, as you move further away from us, suddenly all the galaxies are moving faster and faster away from us. and if you draw a straight line through this is kind of the average trend, okay? Further and further you look from it. Now, on small scales, galaxies are just moving relative to each other randomly, just like stars in our own Milky Way are moving randomly relative to each other. But if you zoom out, on average, the stars are rotating around our Milky Way. Similarly, if you zoom out to galaxies, on average, they're moving away from each other. That's what this means. And the slope of this line is called the Hubble constant. It tells us how far you have to go away from us. You know, for any distance you move away from us, galaxies are moving this much faster away from us. Now, Hubble's data from 1929 covers this little red area, but we can use supernovae because remember, those are a standard candle. We know exactly how bright a supernova is, so we can determine their distance. And they are so bright, we can see them even in distant galaxies. So we can use these supernovae to continue learning about Hubble's law and extending it to 1 billion light years away from us, okay? And this law is incredibly accurate. You see, even going to 1 billion light years away from us, Hubble's law, you know, the further away you go, the faster galaxies are moving away from us. Okay? So here's just a kind of a cartoon of what we're talking about. Distance along the x-axis, the further something is from us, the faster it's moving away from us. How do we know how fast they're moving away from us? Redshift. It's how red the galaxy is. The modern value of this Hubble parameter, that's the slope of this, is 70 kilometers per second. So that's a speed, 70 kilometers per second for every million parsecs. So if you go 1 million parsecs away from us, so that's about 3 million light years. So if you go about 3 million light years away and look at a galaxy, it's going to be moving 70 kilometers per second away from us. You go twice as far, it's going to go twice as fast away from us. The further you get away, the faster things are moving away from any other point in the universe. The universe is expanding. That's what this is telling us. Okay. And so that extends us out to the very edges of the known universe. As far as we know, and we'll talk about this more later, as far as we know, the universe could be infinite in extent, but we can only see a given amount of it because everything's moving away from each other. And at a certain point, that means that things are so redshifted that we can't see them anymore. But as far as we can see these super powerful supernovae going off every once in a while, like popcorn in distant galaxies, showing us how far they are. And we see the redshift telling us that they're moving away from us. Okay? And so we have a way, ultimately, though, of cross-checking Hubble's law and telling that it's so accurate, we don't even need to see supernovae. We can just trust. If we see a galaxy's velocity through redshift, we know how far away from us it is. So this is one of the pinnacles laws in cosmology that we use all the time. You just look at a galaxy, you see how red it is, and you know how far away from us it is.
Red far.
So as a reminder, I do want to mention, right, this one way of cross-checking Hubble's laws with type 1a supernovae. Remember, this is this violent explosion of a white dwarf star. This is, you have a low mass star that has died and created a white dwarf. That's like this core of carbon. Remember? But remember, what can happen is that white dwarf can exceed the 1.4 solar mass limit, beyond which it can collapse and suddenly fuse all of that carbon. Okay, that's called a type 1a supernova, and they're all tend to be about the same luminosity, about 4 billion times the luminosity of the sun. So suddenly, once you reach the Chandrasekhar limit, that's the name for it, about 1.4 solar masses. And this can happen if you have a companion binary star that's some of whose material is falling into the white dwarf, and then suddenly it exceeds this mass limit. That crushing force is able to suddenly fuse all of that carbon, releasing a tremendous amount of energy. Here's a few examples. So this is a distant galaxy, right? And like most distant galaxies, all you can see is this faint kind of milky glow, just like in our own Milky Way. Milky glow representing the combined brightness of billions of stars all together. And normally you can't see an individual star in a distant galaxy, except like this. Suddenly you have a supernova where for a few days or so, it totally outshines all the other stars in the entire galaxy. There's another example with little arrows pointing to it. And some of these other star-like things, remember, those are the stars we're looking through from our own Milky Way. But this is a star in that actual faraway galaxy that suddenly went supernova. And, you know, this is one of the ways we, in modern times, can very accurately establish this Hubble parameter. So well, we not only use type 1a supernovae, which are shown in green, we also use type 2 supernovae, and some other technical cross checks. All of them agree with this value of roughly 70 kilometers per second for every, you know, the galaxies are moving away from us, 70 kilometers per second for every roughly, remember, million parsecs, okay, which is about 3 million light years. So remember, supernovae are pretty rare. So luckily, Hubble's law seems to be so accurate for large distances. We don't have to see supernovae. We can just trust. The redder a galaxy is, in other words, the faster it's moving away from us, the further away it is. Okay, that's Hubble's law being used. Now, I'm going to skip this one. Suppose you observe a galaxy moving away from you at 0.1 light years per year. Okay, that's a speed. So a tenth of a light year every year is how fast it's moving away from you. And it's now 1.4 billion light years away from you. Okay, how long has it taken to get there? The answer is 14 billion years. If you
Oh,
have
rounded.
something, so this is using this formula here, right? In physics, we have a very important and useful formula, which is that distance is related to velocity and time. If you know the velocity and time, you multiply velocity by time to get distance, or if you can solve for time. If you know the distance and the velocity, you can solve for time. So that's what we're using
Oh, you
here.
divide it.
We know the velocity, we know the time, we know the distance. So 1.4 is the distance, divided by 0.1 is the velocity, gives 14 billion years. And this is how we determine the age of the universe. This is using Hubble's law, because we're using the fact that things have a bulk. These distant galaxies are moving away from us, okay, at some velocity that we can measure, okay? Hubble discovered this fact that the universe seems to be expanding, but if we were to rewind that backwards, what we're calculating here is how long it would have taken for everything to get back together, okay? And we call that the Big Bang. And it appears from this calculation that 14 billion years ago, everything was together, okay? It took 14 billion years going that speed for the galaxies to get that far apart. And that's what we see when we do this calculation for distant galaxies. So all signs point, anywhere we look in the sky, galaxies are moving away from us. We measure their distance and velocity. We determine that they've been expanding away for about 14 billion years. And that's the age, we say, of the universe. Any questions? Now, I do want to briefly touch on galaxy evolution before moving on to trying to cover some material from the next lecture, because we're a little bit behind. But I just want to mention that we can, while we can never watch a galaxy evolve, because it takes billions of years for a galaxy to evolve from the beginning of the Big Bang, what we can do is look back in time by looking further and further away from us in order to see galaxies at earlier stages of their lives, because the farther away we look, the longer it's taken light to reach us. We are essentially looking back in time. The further something is, we're seeing light. Just so the nearest, well, let's take the moon. The moon it takes about a second for light to reach us from the moon. So if you look at the moon, you're seeing the moon as it was 1 second ago. For the sun, it takes about 8 minutes for light to reach us. So when you look at the sun, you're seeing the sun as it was 8 minutes ago. The nearest star, about 4 light years away. You're seeing Alpha Centauri, the nearest star, as it was 4 years ago. And if you look at a distant galaxy, say 11 billion light years away, you're seeing it as it was 11 billion years ago. So because of that, we can see galaxies in early stages of their development, or look at nearby galaxies and see galaxies in later stages of their development. We can also do simulations, and this is one of the primary tools we use. We compare simulations of, let a bunch of matter loose and watch what it does as it forms stars and galaxies, and then compare it to what we see. One thing that we see that's common is one of the things that primarily defines different shapes of galaxies that we see is the fact that sometimes they can collide. So here are galaxies do interact, they collide, and that changes their shape. Here is a simulation in the upper left compared to an actual image from Hubble. So you're seeing a simulation of 2 galaxies colliding. It's very similar to what you see in Hubble. And the largest collaboration that's doing simulations is called the TNG collaboration. It has done simulations of the universe over hundreds of millions of light years across. And when you do these simulations, you get these sort of web-like structures representing clusters and superclusters of galaxies that tends to match up pretty well to what we actually see when we look out at the largest distances in the universe. Here's this collaboration, the TNG collaboration. Here is just a selection of numerous galaxy types they see when they do let these simulations run. They see spiral galaxies, they see elliptical galaxies, they see barred spiral galaxies, and they see irregular galaxies. This is still an area of pretty active research. There's still all sorts of competing theories about what causes certain galaxies to look different ways, but this is the main research program that's driving these theories. Is comparing these simulations to what we actually see. And they're pretty good now. We really do a simulation, you see some spirals, some ellipticals, irregulars. It's really cool. One more thing I did want to mention just on the topic of galaxies is that there's a particular signal that we get from galaxies. We call these active galaxies, where we look kind of at the center of a galaxy. It's very, very bright. We call these active galactic nuclei. We look in the center of a galaxy, call it a nucleus, and there's a region about the size of the solar system that's unusually bright. And we talked about this in our own galaxy. There's like a solar system size region where there's a bunch of stuff, a bunch of radio waves, a bunch of X-rays coming out of it that we think is a supermassive black hole. We see the same thing in some other galaxies. About 1% of galaxies have what we think is a supermassive black hole in the center. And one common type we have a name for called quasars. Okay, it's called quasi. It stands for quasi-stellar radio source because these are the most luminous objects in the universe. Okay, the center of these galaxies, where they're these supermassive black holes, are more than 100 trillion times as bright as the sun. Okay, that's brighter than a supernova, and they're always. It's not just for a few days. They're always that bright. That's because they have some supermassive black hole in this center. So these are some of the furthest objects we can see in the universe, are these galaxies that are emitting radio waves from their centers. Here's some examples of active galaxies, and what you often see. So here's the galaxy: is they're emitting these plumes out into the interstellar medium or intergalactic medium, because you imagine the supermassive black hole rotating along the poles, it's sending out these jets. Here's Centaurus A. Here's viewed in visible light, but here, when you add radio waves, you see these beautiful kind of, we call them lobes, signal from this supermassive black hole in the center. There's kind of a nice compilation showing different colors where they're coming from: optical, radio, and X-ray, and then all combined. And I mentioned that the most distant known things we can see in the universe are quasars because they're so bright. So here we're looking at it. It's red. Okay, it's super redshifted because it's very far away. It's the most distant known quasar. This is from less than 1 billion years after the Big Bang. So we're seeing this literally from something 13 billion years ago. Extremely distant, and it's extremely redshift because it's moving so quickly away from us. We're going to shift to talking a little bit about cosmology now. Are there any questions about galaxies? So I want to introduce you to one of the first major, or just one of the typical questions you might ask when it comes to thinking about cosmological questions. Okay. Those questions concerning the universe as a whole. It's called Olber's paradox. This question is, why is the sky dark? Okay. it's natural to suspect, and as far as we know, it's possibly true, that the universe is infinite. So if you imagine, say, an infinite, eternal universe where there's been stars, say, extending infinitely far away that have been there forever, didn't just suddenly pop into existence. It's natural to ask, why is the sky dark? Why would you ask that? Well, imagine looking out at the sky and you count up all the nearby stars. Okay, the nearby stars are closer, so they take up more of the sky. So here I've drawn some random nearby stars, say 3 light years away. But then you imagine more distant stars. Okay, so now we're going out twice as far, and then twice as far again. You add more distant stars. Keep going further and further away. You add more and more distant stars. Well, eventually, if you keep adding stars, it's like looking through trees in a forest. If you keep adding more and more forest, eventually, anywhere you look, there's going to be a star. And this is true. This is this would be true if we were talking about an infinite, unchanging universe that's infinitely old. It is true that the sky wouldn't be dark; it would be white, bright. Okay, so this is kind of a paradox if you think that perhaps the universe has been around forever, and so this is one reason why we know the universe hasn't been around forever. And I know some people are concerned about their grades. Today, I'm just going to help walk you through the answers to any questions there are. So let's do a poll question. This is Olber's paradox. So Olber's paradox is a simple question. Why is the sky dark? And its resolution suggests the universe is finite in age. It's not infinitely old. What's the simple question posed by Olber's paradox? It's why is the sky dark? Okay, that's the question. So the answer is D. And it tells us that, well, the reason why the sky isn't dark is because all the stars, if we imagine looking out infinitely far, all the stars that would be there that would make the sky white bright are not, they haven't been there forever. If we look back in time, as we look further and further away, the stars haven't been born yet. Okay. So this kind of brings us to this question, this idea of the Big Bang. Okay. 14 billion years ago, the universe was hot and dense, and it's been expanding ever since. This is something Hubble's law kind of suggests. Anywhere we look, everything's moving away from everything else. And since that time, 14 billion years ago, the universe has been cooling off. Stars have begun to form. And so if we look far away, we're never going to see a star more than 14 billion years away. We're never going to see light years away. We're never going to see a galaxy more than 14 billion light years away. Why? Because it wouldn't have formed yet. Because the further away we look, we're looking backward in time. So that's the resolution of Olber's paradox. The universe is not infinitely old. In fact, it's 14 billion years old. And ever since then, it's been expanding away. All right. Everyone get a chance to answer the question? I'm going to end the poll. I see some people may not have been paying attention when I was just giving the answer. Okay, I'm going to end the poll. Okay, as I explained, the answer is D. Why is the sky dark at night? So this brings us to the Big Bang. This is this theory, the major theory of cosmology, explaining the evolution of our universe as a whole. Okay, that is about 14 billion years ago. What we know now, we don't know. In physics, we don't like to say what we don't know. We don't know exactly how the universe began or what was before the universe. What we do know is that 14 billion years ago, the universe was hot and dense. And since then, it's been expanding. Okay. We're going to talk about two ideas that are central to the idea of this Big Bang theory. One is general relativity. We already did introduce you to that. Okay, general relativity is also known as Einstein's theory of general relativity, says that everything that we know exists in what's called space-time. Okay? And space-time can be curved, and matter, like planets, stars, galaxies, curves space-time. And the curvature determines how matter moves. Matter follows straight lines. We call them geodesics in curved space. Okay? As a reminder, this piece of paper, because it's just, if I draw a straight line, I just drew a straight line on this piece of paper, right? But then if I curve space by making a little tear in this piece of paper and then hooking it back together, so now space is curved. So now in curved space, that line is kind of curved around. That's the basic idea. That's general relativity. And in general relativity, we have a way to explain why space is expanding. Okay, and we'll talk about that. It's called the energy density of the universe and the curvature of the universe. So how curved the universe is also determines its rate of expansion. So this is something we'll talk about on Wednesday. Another principle is called the cosmological principle, and it seems to be true. On large scales, if you zoom out really, really far, the universe is homogeneous and isotropic. Okay, what does that mean? It means that any direction you look, this is isotropic. Any direction you look is about the same. So it's not, if you look any direction in the sky, it's not like suddenly you look, to the east and the sky is filled with galaxies, and you look to the west and there's hardly any. No, any direction and the universe looks on average the same. And homogeneous means any location in the universe. If you shift us 100 million light years this way or this way or this way, the universe on average looks the same. Here's just an example, like a brick wall like this would be an example of something that's homogeneous. You shift to the left, up, down, looks the same. It's not isotropic though, because there's preferred directions, like the left-right is kind of special because you can get look left-right and you're kind of in one of these like divisions between the bricks. Okay. Here's an example that's both kind of homogeneous and isotropic, and this is kind of what the universe looks like on large scales. Any direction looks about the same, and if you just move any direction, left, right, up, down, it looks about the same. So, in other words, the matter in the universe is evenly distributed. It's a less fancy way of saying the same thing, and with no center, no edge, no preferred direction. These are the basics of the theory of the Big Bang. Okay, what's the evidence for the Big Bang? Well, we talked about Hubble's law. The universe is expanding, seems to be expanding uniformly in all directions. Any direction we look, the further away something is, the faster it's moving away from us. This tells us it's expanding uniformly. I'll give an example like this. You can do an experiment yourself to prove this to yourself. If you put like marker dots on a balloon, blow the balloon up, the marker dots will follow Hubble's law. Mm-hmm. You'll see the dots will move away from each other as you blow the balloon up, but also the further away you look, the faster dots are moving away from each other. Oh. Okay, so Hubble's law is a big piece of evidence for the Big Bang. We will also go over what's called the cosmic microwave background, that sounds maybe like a boring technical term, but it's kind of amazing. That is the light that we are still seeing. It's still reaching us from any direction. That is the light from the Big Bang itself, still reaching us, called the cosmic microwave background. Now, the Big Bang was very hot, but this light that's reaching us has been redshift, right? Because that light from that hot Big Bang, just like faraway galaxies have been redshift, has been stretched into the microwave type of light, the same type of light that is used by cell phones, and so you don't really notice it, right? It's called the cosmic microwave background. And another piece of evidence we'll talk about is called Big Bang nucleosynthesis, or BBN. And this is the theory of how the universe started out with a bunch of hydrogen and helium. Right? Remember, our solar system, it's mostly hydrogen and helium. Interstellar medium, mostly hydrogen and helium. All the other stuff is stuff formed in stars through stellar nucleosynthesis. Right? We talked about how stars form carbon, for example, or iron. The Big Bang theory successfully explains why we get mostly hydrogen and about a quarter helium out of the Big Bang. The simplest elements came directly out of the Big Bang as the universe expanded and cooled from its initial hot, dense state 14 billion years ago. Here is kind of a cartoon explaining the history right after the Big Bang. This is showing that, there's a point right after the Big Bang, fraction of a second, about 10 to the minus 40 seconds after the Big Bang. So extremely small fraction of a second, where we just have no idea anymore. We don't know the laws of physics at that point. We don't know what happened before that. Okay, that's as far back as we can extrapolate to. Okay. After that, there were periods like where the universe continued to cool off. And as something cools off, things can begin to snap together. You can eventually form subatomic particles. You can eventually snap together to form nuclei like hydrogen and helium. And eventually it cools off enough that you can form whole elements. Electrons snap to protons to form neutral atoms. Electrons snap to helium nuclei to form stable neutral helium. And that's the part where light is able to roam freely. That's the point where we see that light from that time still glowing from the Big Bang. From that point where light was released to move freely through the universe. And that's the light we are still seeing from that moment, about 100,000 years after the Big Bang. Any direction we look, we're still seeing light from the Big Bang, because remember, if you look at far away enough, you're looking back in time. So this light, it's just light from 14 billion years away. So it's just now reaching from the Big Bang, any direction we look. Here, focusing more on some later times. So I just talked about that afterglow light pattern, the cosmic microwave background at 38. Well, it's about 300,000 years after the light, after the Big Bang. Then there was a period where the universe was too hot still to form stars, right? Remember, you have to have clouds of gas and dust cool down so you can contract and form stars. And these are called the dark ages. The first stars eventually, with the things cooling off as the universe continues to expand, the first stars formed about 400 million years after the Big Bang. And that's when you first began to form galaxies. And since then, the universe has just continued to expand for the last 14 billion years. And now, so a topic we'll cover in the next few lectures is that the universe is actually starting to expand faster and faster. It's actually accelerating. So that's what you kind of see here. The universe has been expanding. It's going to accelerate. This is due to what's called dark energy. Energy inside the fabric of space itself, pushing it to want to expand. Any questions so far about these ideas? Okay, here's another just total freebie. So I'm going to ask this as a poll question. Okay. So the universe is. Oh, here we go. This is the one. So here is a question. It's not the one I'm asking. The universe is doing what? It's expanding and cooling. So early in the history of the universe. Sorry, my trackpad's not working well. Early in the history of the universe, what was it? And I'm helping you here. It was hotter and denser. Okay? That's kind of what the Big Bang Theory tells us. The universe started out early, hot and dense, and since then it's been expanding and cooling. Okay? So the answer here is A, hotter and dense. And again, I'm just trying to give you some free points to help you succeed in this course. I'll give you 5 more seconds, and I'm going to end the poll. Okay. There we go. Correct answer was A. The universe was hotter and denser. All right, the next thing I'm going to do, I think I'm going to do this when we get back on Wednesday, is just remind you about Hubble's law. But I think I'll let you off here today. Are there any questions? All right. Everyone, I'll see you on Wednesday. Have a good couple days.
Thank you. Have a good day.
Thank you.
Thank you.